for the test, you do need to know what the first law of thermodynamics is, what the second law is, and also the zeroth law. And the important thing about thermodynamics is that you need to know how to calculate heat for different processes. And we mentioned, let me see, do I use this? Okay, we mentioned that when you have a non-gas, let's say liquid, for non-gas material like liquid or solid, then the amount of heat during any process is equal to, using the following equation, the mass of the object times the specific heat of the object, and then times temperature change, if there's a temperature change, and then plus or minus the mass of the object that undergoes phase transition, if there is phase transition. Okay, so in other words, for all non-gas processes, for not all for non-gas materials like solid, liquid, this is the equation that you want to use to calculate the amount of heat. When the process involves temperature change or involves the phase change. So mass times specific heat times the temperature change plus or minus mass of the object that undergoes phase transition, and L is the heat transformation. So it can be the heat of vaporization or heat of fusion, depending on which phase transition that's being taking place. Okay, so as I mentioned to you in class, you do want to make sure that everything is in SI unit so that you won't make mistake. So in this case, even though the temperature might be given in Celsius, you do want to change that to Kelvin. We know that temperature in Kelvin basically is equal to the temperature in Celsius plus 273. That's a conversion, and you'll be dealing with most of the temperature in Celsius. And of course, we also mentioned in class that the change, the conversion from temperature in Celsius to Fahrenheit. So those are the equations that you might want to include on your formula sheet as well. And this equation gives you the temperature as in Kelvin. Okay, and so like I mentioned, this is this is when there's a temperature change, and there are processes when there's a phase transition. Then it does not. Then the temperature will stay the same during the phase transition, but there's a heat exchange, and the heat exchange is m times L. Okay, so we have the heat of fusion and the heat of vaporization. Now, when do you use plus or minus? So, like I mentioned, if this is solid, if the direction of the transition going from solid to liquid to gas, then you use plus because in order from solid to change to liquid, it requires more energy, and for molecules in liquid form to become gaseous form, then it requires more energy as well. Okay, and so during this process from solid to liquid involves a heat of fusion, and from liquid to gas involves heat of vaporization. So it depends on which phase transition that's being taken place. Now, if the direction is from gas to liquid, from liquid to solid, then you use minus in this equation. Okay, so the plus or minus depending on the directions of the phase transition. So this is the equation to calculate. This is the equation. This is the equation to calculate the heat. And like I mentioned, you also need to know how to calculate the entropy change. Now, for non-gas material, the entropy change, of course, based on the heat exchange, you can actually derive that the entropy change should also involve two terms. One when the process involves a temperature change, and the other one is when the phase transition is taking place. So delta S is equal to the mass of the object times the specific heat of the object, and then times the natural log of temperature ratio. And the temperature ratio is the final temperature over the initial temperature. And then plus or minus, because again, this plus or minus, comes from this plus or minus here in the heat equation. Plus or minus mass of the object that undergoes phase transition times the heat of transformation over the temperature, and that temperature will be the temperature when the phase transition is taking place. In other words, that will be the when the temperature does not change. Okay. Now in this equation, you want to make sure that the temperature are definitely in Kelvin. Okay, you cannot use the temperature in Celsius. If you use the temperature in Celsius, then you'll get wrong answers. So you have to remember to convert temperature to Kelvin, and then use this equation to calculate the entropy change when there's either a temperature change or the phase change. Okay. So this is basically the important things from chapter 18. We also mentioned, in chapter 18 that when there's a thermal expansion, then you need to know how to calculate the size or the dimensions of the object changes due to the change of temperature. So in this case, let's say you have, if the expansion due to temperature change is only one dimensional, then you have delta L, which is the change in length, that will be equal to the original length times the coefficient of thermal expansion alpha, and then times the temperature change delta T. Okay, so usually alpha, the coefficient of thermal expansion usually will be given, and temperature change, and then you have the original length. Then you can calculate the change in length. That's just delta L. Okay, and of course, depending on delta T is positive or negative, your delta L can be positive or negative. So the total length will be, so the modified length due to the change of temperature, of course, will be the original length plus delta L. Okay, this is due to the change of temperature. Now we also mentioned that when you're dealing with three-dimensional objects, then when there's a temperature change, the change in length will happen in three-dimensional. So you have delta V, the change in volume. Your delta V can be calculated using this equation. That will be the original volume, and then times the beta, the coefficient of thermal expansion for coefficient of volume expansion, and then times delta T. Okay, and most of the time your beta, that coefficient will just be 3 times the alpha, and your total volume now, due to the temperature change, will be the original volume times delta V. And again, you can see that your delta V can be positive or negative depending on the sign of your delta T. Okay, so this is the important thing from chapter 18 when you're dealing with non-gas material. Now, when you're dealing with gases and stuff, then you still follow the similar thing, and you also need to remember the first law of thermodynamics, because we use it a lot when we talk about gas, when we're dealing with the gas. So the first law of thermodynamics is the change in internal energy is equal to the amount of heat that's added to the system minus the work done by the system. Okay, so this is a change in internal energy, and you'll find out the first law of thermodynamics is very useful, especially when you want to apply it to a cycle like an engine. Then a lot of time we use the internal energy. We use the first law of thermodynamics. Now, when we deal with when we deal ideal gas, we know that PV equals nRT is a very useful equation. You always want to use that when you want to calculate the state of the gas. Let's say state of the gas, it means that when you're asked to find temperature, either temperature, volume, or pressure, then ideal gas law is the one to go by. So this is ideal gas law as long as it says that the gas is ideal gas. Okay. Now, there's a one additional equation that you can use when you're dealing with an ideal gas that undergoes adiabatic, and that is when you have PV gamma, that is a constant. When that equals a constant, you can say that the initial pressure times the initial volume to the factor of gamma is equal to PF and then VF to the gamma. Okay, this is ideal gas and adiabatic. Okay. Okay. So when we talk about a cycle or on the PV diagram, you have all kinds of processes. You need to know, there are a couple of processes that you often encounter. Let's say a constant volume. When you're dealing with constant volume, when you read constant volume, it means that work is zero. Okay, and also your Q, because this is a constant volume process, so your Q should be equal to NCV and then times delta T. M here, of course, is the number of moles of the gas. CV is the specific heat of a constant volume, and delta T is the temperature change. Okay, so when you're dealing with constant volume process, W is 0, Q is equal to NCV times delta T, and likewise, that is also, if you apply the first law of thermodynamics, you'll find that that's also equal to the change in internal energy, right? When you look at the first law of thermodynamics. Okay, so this is constant volume process. We have a constant pressure process. Then the work is equal to pressure times delta V, the change in volume, and your Q, when you are dealing with a constant pressure, is NCP, and then times delta T. Okay, so what is our change in internal energy? The change in internal energy for all processes is still equal to NCV delta T. Okay, so you can see that you have the constant pressure. Work is P times delta V. Q is equal to NCP delta T, and the change in internal energy still remains the same as NCV delta T. It only depends on the change in temperature and at the specific constant volume. And when you have constant temperature, isothermal process, which is constant temperature. Okay, constant temperature meaning that it is isothermal. When it is isothermal process, then let's see. For isothermal process, your work, we derived that in class. The amount of work can be calculated using this equation, the nRT, and then natural log final volume over initial volume. Okay, and your Q is equal to, actually your Q will be just equal to that as well, because if you apply the first law of thermodynamics and realizing that the internal energy, the change in internal energy has to be zero because it is an isothermal process, then your W is equal to Q. Okay, so this is for constant temperature process. Now, when you have adiabatic process, which means that there's no Q, so your Q must be equal to 0, and your W, and let me just say that Q is equal to 0, and so your W, the change in internal energy, which again is equal to NCV delta T, and that's also equal to negative W when you're dealing with when you apply the first law of thermodynamics. And yeah, so just take it yeah, just like that. Okay, and of course, if you want to calculate work, you can use the definition for a adiabatic process. It is a little bit more involved because you have to use calculus to calculate that. I mean, take for example, you had W, that's defined as your PDV, right? And then if this is ideal gas law, then what you can do is that you know, you can express P in terms of nRT over V, or you can also use the PV to the gamma, that equation, and then plug into the to this you know, expression to calculate amount of work. Or if you prefer, you can actually use the NCV delta T to calculate the change in internal energy. I think that's an easier way to do it, so long as you know the temperature change. Okay. So this tells you the you know, for different processes you have different you know, there are different equations to calculate either work, heat, or internal energy. And you can see that the first law of thermodynamic is very useful because you have three parameters. As long as you know two of them, then the other one you don't have to calculate it. You can just use the first law, and you can deduce the third unknown ones. Okay, so that is that. And as I mentioned, the change in internal energy is always equal to NCV delta T, regardless what kind of process that is involved, because temperature, because internal energy only depends on temperature. So if you want to calculate internal energy, you can simply just use number of moles times the specific heat constant volume and times the temperature. Okay, so that is that. And also we mentioned about the kinetic energy. The average kinetic energy basically only depends on temperature, and that's 3/2 Boltzmann constant, and then times that temperature. So that's that. And we also mentioned that for gases, if you want to calculate the entropy change, you have to use this equation, and that's equal to number of moles times the gas constant, and then times the volume ratio. So that's final volume over the initial volume, and then plus the number of moles times the specific heat constant volume, and then times the natural log of the temperature ratio. So it depends on what kind of process that's involved. You might have the contribution from both two terms, or they are, you know, if they are processes that say constant volume process. For constant volume process, then the first term will give you 0. When you have an isothermal process, then the second term will give you 0. So it really depends on what kind of process, and you can use this equation to calculate the entropy change. Okay, so let's see. And also, speaking of the specific heat, when you do problems, make sure that you you know, you pick up the words whether the gas is monatomic, diatomic, or polyatomic. So for we know that CV and CP CP and CV, they differ by 1 R. So if you know the CV value, then the CP value will change automatically because CP is equal to CV plus R. So it is important for you to know what CV value is. So when you're dealing with monatomic, then your Cv is 5.R, 3 halves, okay? And when you're dealing with diatomic, then that becomes 2 5s R. So this is monatomic, and this is diatomic. And so once you know the Cp and Cp value, then you can calculate your Cp value. And the other quantity that you might also need to calculate is your gamma, which is defined as Cp over Cv. So you can see that your gamma value will be different depending on whether the gas is monatomic or diatomic, because your Cp and Cv value will be different for different gases. Let's see. That's that. Now the other thing we discussed in class is that there are different kinds of velocities that you can calculate using Boltzmann's, using Maxwell's velocity speed distribution law. And what we found is that the most probable velocity, which is that the majority of the molecules that will have the same velocity, is calculated using this equation. 2 times the gas constant times the temperature in Kelvin over the molar mass. The molar mass has to be in kilogram. So this is the most probable velocity. And we also calculate the root mean square value. So the root mean square value is equal to 3 times RT over the molar mass. We also mentioned about the average velocity of the molecule. So the average velocity of the molecule is equal to ART, and then over pi times the molar mass. Okay, so those are three velocities that three speeds that we discussed in class. And now we also mentioned about engines and also the refrigerator. So what you need to know is that for all cycles, what is BP? That's the most probable velocity. Most probable velocity, which is the majority of the molecules will have. The cycle. So whenever we're dealing with a cycle, we know that after cycle, the internal energy change has to be 0. And we also know that the entropy change must be 0. Okay? And that is because after cycle, the engine get back to its original starting place. So it has the same temperature, same volume, same pressure. So that's why there's no change in internal energy and there's no change in entropy. Okay. And so when you're dealing with a cycle, then you have to go back to this chart to see what kind of process that's what kind of process that you're dealing with, and apply these equations in order to calculate the amount of heat that's being exchanged or the amount of work that's done by the engine. And so the second law of thermodynamics, of course, is very elegant. It just says that the change in entropy must be equal or greater than 0 for an isolated system. Okay, and for reversible processes, delta S is equal to 0. For irreversible process, then delta S has to be greater than 0. Now, for a cycle, ideally, for ideal engines, we're assuming that it is repeatable, reversible. So that's why the entropy change is equal to 0. And we defined thermal efficiency for an engine, epsilon, and that's equal to the amount of work that's done by the engine divided by the amount of heat that's been added to the system. Okay, and as we done problems in class, you'll find that the heat that's being added to the system may not be just doing one process. There might be two segments of the cycle that involves the heat added to the system. Okay, so this is a definition of the thermal efficiency, the amount of work done by the amount of work done by um, amount of work done by the engine divided by the amount of heat that's being added, the amount of energy that's being added as heat. Okay, so how do we calculate work? Again, when you apply first law of thermodynamics, net work is equal to net heat, because after cycle, there's no change in internal energy, so net work is equal to net heat. So the net heat involves positive heat and negative heat. So when you add it together, the amount of work will definitely be less than the amount of positive work that's done by that's being added to the system, because there's negative heat, or the heat that's being lost by engine to the environment. So this is the thermal efficiency. And we also mentioned about the thermal efficiency for Carnot engine. Now for Carnot engine, we know that there'll be your W, which is the sum of all the heat, which is the heat added to the system minus the heat that's being lost to the low temperature reservoir, that's W, and over the amount of heat that's added to the system. So what I found here is that if we are dealing with a Carnot cycle, then this equation can be represented by the temperature on the two isotherms. So we have 1 minus the temperature of the lower temperature isotherm temperature, and that's over TH, the temperature of the high temperature reservoir. So it's 1 minus TL over TH. This is only valid when you're dealing with a Carnot cycle. For the generic, for any general engine, this is the equation to go by. This is when you're dealing with the Carnot engine. Okay, so that's the thermal efficiency, and we also mentioned about the coefficient of performance, which is when you're dealing with refrigerator, so coefficient of performance of a refrigerator. And that is your K, and that is defined as the heat extracted from the low temperature reservoir over the amount of work that's done over the amount of work that has to be done in order to extract the heat. Okay, so so I think that's basically it. Do we have any questions? These are all the important concepts, and so what you need to do is learn how to apply those equations and concepts to the problems that we've done in class and the quizzes that we had in class. Any questions? Okay, I'm actually going to stop the recording so that so it won't take up the memory. Let me see.